Hey class, Adam Ward here. I want to talk to you today about colloidal particles, or colloids, as one of the things that we are going to be removing in all of our drinking water treatment operations. Alright, so off the bat here, what are we talking about when we say colloidal particles, or more colloquially, these would be called colloids? What we're talking about in terms of colloids are very small particles. So these might range in size from 1 nanometer to 1 micron. And so these are not, we're not thinking of big granular material like sand. We're thinking more like clays and extremely fine particles in the water. Now, we care about this in terms of drinking water treatment because there are several constituents that are in this size range that are things we might not want to pass on downstream to our customers. And so those can include various microorganisms, pathogens, algae, clays and silts, and trace organics. Some of those you can imagine are direct health risks, things like pathogens and some microorganisms. Others, like trace organics and clays, will affect the color and the taste of our water. Even if it's healthy to drink, it's not preferable to customers. And so we have an added step in our treatment process because, well, we want to get rid of these, and given enough time they might settle out. They don't settle efficiently. So we would need extremely large reactors or basins for these very small particles with their extremely small settling velocities to get out of our water column. And so instead, we go through a couple of steps, one of which is called flocculation, and this is basically getting the colloids to stick to one another to form larger particles, and then sedimentation, where we let them settle out efficiently now that we've made them larger than they were at their intake. So to understand colloids and what we're doing here, I want to zoom in and just give you a sense of what these colloids look like and why the different options work. So here what we can see is a colloidal particle, and I'm highlighting here in red. Most of the colloids that we're going to worry about have ultimately have very large surface areas relative to their volume, and they develop a bulk negative charge around the edge of the colloid. Now, because there's this negative charge on the edge of the colloid, then we can envision that immediately outside of it there's this zone that has a positive charge. It's basically stuck there. It's an electrostatic force holding that positive layer or stern layer in place. And then we've got some diffuse layer that's more positive than negative before we get out to the bulk of the solution. Now, those charges become important and structure become important because it prevents our colloids from conglomerating or agglomerating to one another and settling out. And so in between our two colloids, there's two kinds of forces happening. We've got van der Waals forces, which broadly are pulling the colloids together and would lead to them aggregating, forming larger particles, or agglomerating and ultimately settling out by gravity. But that doesn't happen for colloids without human intervention in this process, because we've also got electrostatic forces that are repelling them. So you're trying to push two positive poles of magnets together, for example. And so the strategy then to get rid of colloids is you've either got to crank up the attractive forces or you've got to eliminate the repulsive forces in order to get these things to clump together into bigger groups. Those bigger groups will be heavier and they'll settle faster. So we have basically 4 strategies that we can use to try and destabilize these colloids, get them to agglomerate, meaning clump together, and get those clumps to ultimately settle out. So today is all about how do we destabilize these colloids. And we'll look through here 4 major options. Okay, so option 1, we can try to get rid of the repulsive forces. And one way that you can do that is you can raise the ionic strength of the solution. And so the idea here is we could add enough free ions into the solution that it would ultimately cause a compression of that sort of more positive than negative layer around the colloidal particle itself. However, if you do that, you have to add a whole lot of material to the solution, and you're still left then with a fairly salty solution. Even though you've gotten rid of the colloids, you might now have a lot of free ions floating around you need to deal with. So you can imagine dissolving a whole bunch of cations and anions in there. And so this is not a strategy that we use, although it is a strategy that is possible. Option 2 is adsorption and charge neutralization. And so what we can do is we try to add something with a positive charge that will adsorb onto the colloid surface. And by doing that, we're going to reduce that net negative charge, we'll reduce the cloud of positive charge around it, and we'll let those particles get closer together. So what this might look like is adding, and it's often a multivalent metal of some sort or another, and here I'm drawing an aluminum hydroxide, which has a net positive charge, and so electrostatic forces will cause that to stick onto the edge of that colloidal particle. So the result of doing this, repulsive forces between colloids go down. That should let them agglomerate on their own, start to stick together into larger groupings, and ultimately be able to settle out. Two more options then. Option 3, attachment and interparticle bridging. And so this involves long chain polymers, and well, you'll probably never hear someone talk about it this way. The short of what we're trying to do is we're trying to glue the colloids together. So we're adding long chain polymers that have some bonding sites on them, so some functional groups where those negatively charged colloidal particles will want to stick. And the idea is that rather than overcoming their forces between one another, we get them all to stick onto this long chain polymer, and then that long chain polymer that's holding them will ultimately settle out along with them. This is absolutely doable. Those polymers can be somewhat expensive, but this is a viable option. And lastly is what's called sweep flock. And in option 2, we saw that we could add some positively charged particles to offset some of those negative charges inside of our colloidal particle, or at the surface of our colloidal particle. Option 4, you could think of it as option 2 taken to an extreme level. And so what we're going to do in option 4 is we're going to add so much of, in this case again I'm showing you with aluminum hydroxide, but whatever those green particles are, we're going to add so much of that it's more than the solubility limit. So some of it will actually precipitate and fall out of solution. And because that colloid offers sort of a favorable place for that aluminum hydroxide to stick, what happens is when that precipitate forms, it tends to form on the colloids. And so really the colloid hasn't fundamentally changed. It hasn't necessarily stuck to another colloid. What's happened is it's basically gotten coated with these little precipitate anchors, if you will, that cause it to fall out of solution. So this is what's called a sweep flock approach. Flock short for flocculation, or a flock being a particle that's formed in this way, I should say. Most common in the US is this option 2 and option 4, primarily the sweep flock approach. Far and away, the number one thing that we use is alum, and I'm showing you its chemical formula here is Al2, then it's got 3 sulfate groups, and it's complexed with 4 waters. So alum is a fairly cheap material, it's widely available, it's non-toxic to our downstream water consumers, and it doesn't create any side effects that are so large we can't overcome them with other treatment steps. So the key reaction that takes place for us, that alum got it written out here. So in the first term, that alum is shown. What I'm overlining in blue right now is natural alkalinity in the water. So we do need water that has some of these bicarbonates floating around in it. And what we're going to get out of that on the right-hand side of the equation is 2 of these aluminum 3OH group trihydroxy particles, and I've drawn a down arrow there to indicate those are the thing that will settle, and then a host of other species that'll end up in the water column. And so again, alum shown in red, alkalinity in blue, which is likely already present in the water in sufficient amount to drive this forward, but if it's not, we can basically add alkalinity to the water if we need to, along with our alum. And that AlOH3, that is the particle that settles. That's the colloid, that's the green, that will be coating the colloid. And as a consequence of those settling, they will sweep those colloids along with them. Alright folks, so what I care that you understand here is, so one, that we've got these colloidal particles. We know that they can be a risk to downstream users, both in terms of their health and well-being and their preferences for taste and coloration. And we've got several strategies that rely on our basic chemistry understanding to get these to settle out. The one that we use the most is this approach that I'm showing on this slide, where we're adding alum. And your textbook certainly reviews other metal salts that can be added to the water, but on its basis of sort of cheapness and effectiveness, alum is far and away the standard in the US right now. Alright, so I hope this helps you understand some of the chemistry that underlies the reaction that we need to take place. In class this week, we'll talk about then how do we get this alum in, and how do we create the conditions that allow these flocks to form. So how do we mix and control residence times to let this chemical reaction proceed, and ultimately let the settling proceed to get these colloids out of solution. Thanks for sticking with me, and I'll see you all in the classroom. Have a good one.